My dear students, you were provided with some questions together with their answers on light. Today I shall discuss some topics on light more elaborately for your convenience. Our first topic is refraction. Now the question is, what is refraction? You read refraction in class 8 a bit. Today I'll discuss in more with refraction. The definition of refraction is like that. It is given in your book. When a light ray travels from a homogeneous transparent optical medium to another medium obliquely, it changes its course as well as direction from the surface of separation between the two media. For normal incidents, the light ray changes its velocity only and not the direction. This is called refraction. This definition is given. Now, it is clear that when the light ray travels from one optical medium to another, the refraction occurs. There may be a change of direction, may not be a change of direction. For normal incidents, there will be no change of direction, but change of velocity will occur on all times. So change of velocity is more fundamental for refraction. So whenever a light ray travels from one optical medium to another optical medium, the refraction occurs. Now, one thing, the optical density. What is optical density? We read physical density in class 9. Physical density is the mass per unit volume. You know it. Now, optical density is not like that. It is, for this time I am telling, it is considered with respect to velocity of light. So, greater the velocity of light in a medium, less is its optical density. So, a light travels with smaller velocity in more optically dense medium, and it travels with greater velocity in less optically dense medium. So, optical density can be measured in terms of velocity of light. However, the optical density is measured in terms of refractive index, which will be discussed later. Now, physical density and optical density, they are two different things. But generally, if the physical density of a transmitted medium is more, then optical density is also more. But it is not always true. As for example, if we consider turpentine oil or kerosene oil, it is lighter than water. So physical density of turpentine oil is less than that of water, but optical density of turpentine oil is more than that of water. So it is clear that optical density and physical density are not the same things. Now, optically dense medium and rare medium, I told you. Now, the rules of refraction. There are three rules of refraction. What are those? When a light ray travels from a rare optical medium to a denser one, then it bends toward the normal. You know normal, you read it normal in reflection. Now, whenever light ray travels obliquely or is refracted obliquely from a rare optical medium to a denser one, the refracted ray bends toward the normal. And whenever it travels from a dense optical medium to a rarer one, it bends away from the normal. And for normal incidents, there is no change of course, there is no bending of the light ray. And it can be demonstrated with the help of diagram. You see, in this diagram, this is for when a light ray is traveling from rarer to denser medium. And here you see the refracted is bending to the normal. The original direction of the ray is shown here and is bending toward the normal. And here the angle of incidence is greater than the angle of refraction. And in this diagram, the light ray is traveling from a rare medium to a denser medium to a rarer one, and the refracted is bending away from the normal. And you see, in this case, the angle of incidence is less than the angle of refraction. And for normal incidence, the light ray travels straight without any deviation. In this case, the angle of incidence and angle of incidence both are equal to 0. Now, I tell that these are the rules of refraction. Now, next topic is the laws of refraction. What are the laws of refraction? The first law is similar to that we read in reflection. That is the incident ray, the refracted ray, and the normal to the refracting surface or the surface of separation between the two media at the point of incidence lie on the same plane. So incident ray, refracted ray, and the normal to the refracting surface at the point of incidence lie on the same plane. And obviously this plane is perpendicular to the surface of separation. And this is the first law of refraction. It is given in your book. And the second law is called also known as Snell's law. The Snell's law, in Snell's law, it is told for a particular pair of optical media and for a particular color of light, the ratio of the sine of the angle of incidence to that of the angle of refraction is constant. So it is important. The color of light is mentioned here. For the change of color, it will change. So for a particular color of light and for a definite pair of optical media, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant. Is always constant. And this constant is called refractive index of the second medium with respect to the first medium. This is the name of the constant. Sometimes it is asked in the exam, what is the name of the constant of Snell's law? So name of the constant of Snell's law is refractive index. Is the refractive index of the second medium with respect to the first medium. Now, with the help of diagram, the laws of refraction can be shown clearly. I am drawing the diagram. You try to understand refraction. Suppose these are surface of separation with two media. A light ray is traveling from one medium to another. Suppose from rare medium to denser one, rare to denser one, and here the angle of incidence is this one I, angle of refraction R. So this is a suppose the incident ray AO, refracted ray OB, and normal is NO and dashed. And you see, according to first law, AO, OB, and NO and dashed lie on the same plane. This is the first law of refraction. The first law tells that the angle of incidence AO, so the incident ray AO, the refracted ray OB, and the normal, that is NO and dashed, at the point of incidence O on the surface of separation of the two media, that is refracting surface, all these lie on the same plane. I told you earlier this plane is perpendicular to the refracting surface. And according to second law, for the particular color of light, if this color of light is fixed and the media, optical pair of media is fixed, then the ratio of the sine of the angle of incidence, that is sine I by sine R. Sine of the angle of incidence divided by sine of the angle of refraction, this is constant. And this constant is called, it is represented by the letter mu. You know the word mu. It is represented by the letter mu and it's called refractive mu, or sometimes it is also written as 1 mu 2. There is a refractive index of the second medium with respect to the first medium. This is called refractive index of the second medium. Second medium means in which the refracted ray lies, and the first medium means in which the incident ray lies. So the sine of the angle of incidence divided by sine of the angle of refraction, this ratio is constant if the color of light and the pair of media remain fixed and is represented by 1 mu t and called refractive index of the actually refractive of the second medium, which is written later. Refractive index is second medium 2 with respect to the medium 1. With respect to the medium 1. And this is the name of the constant. Sometimes it is asked in the exam what is the name of the constant of Snell's law. Someone writes it is no mu. It's not the name. Name of the constant is not mu. The name of the constant is refractive index. The refractive index of the second medium with respect to the first medium. As I can tell, AR mu glass. This is refractive index of AR mu glass. We can write like this. AR mu glass, that is refractive index of glass with respect to air. Refractive index of glass with respect to air. The refractive of second medium with respect to first medium. It is written like this. It is called now refractive index. Now on what factor the refractive index depend? Refractive on what factor the refractive index depend? It was this question was given earlier and the answer was also provided with you. And so I am not telling the factor. The factors, I'm just telling the factor. The factors is the nature of the two media and the color of light. Only on these two factors the refractive index depends. Now there are, and one thing is important, the refractive index I told sin I by sin r is equal to refract is the refractive index of the second medium of this part. Now the value of the refractive index can be obtained only for oblique incidence by this formula. By this formula, value of the oblique incidence can be obtained only for oblique incidence. For if the incidence is normal, then both I and R become equal to 0. In that case, it become sin 0 by sin 0 is undefined. So in that case, the value of the refractive index cannot be obtained. So the value of refractive index can be obtained by Snell's law only for oblique incidence, not for normal incidence. This is very important. Now, there are two types of refractive indices. The plural of refractive index is refractive indices. There are two types of refractive indices. These are relative refractive index and absolute refractive index. Now, we will tell them separately. One is relative refractive index. Actually, I told relative index. Relative index means refractive index of one medium with respect to another medium, other than vacuum. The vacuum is not considered here. So, whenever a light ray is refracted from one optical medium to another optical medium obliquely, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is called relative refractive index of the second medium with respect to the first. I told you the AR mu glass, it is a relative refractive index. Water mu glass, relative refractive index. AMUB, relative refractive index. The refractive index of medium B with respect to medium A. So relative refractive index here, two media are considered other than vacuum. Vacuum is not considered here. So whenever a light ray is refracted from any optical medium other than vacuum, from any optical medium to any other optical medium, obliquely, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is called relative refractive index of the second medium with respect to the first medium. Now, what is absolute refractive index? Absolute index is nothing but that first medium is always vacuum. Whenever we tell, let's say, whenever a light ray is refracted from vacuum obliquely from vacuum to any other optical medium, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is called relative refractive index of the second medium with respect to the first medium. I am repeating. Whenever a light ray is refracted obliquely from vacuum to any other optical medium. So you see, the first medium is always vacuum. So whenever a light ray is refracted vacuum obliquely from vacuum to any other optical medium, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is called absolute refractive index of the second medium. In case of oscillate refractive, in case of absolute refractive index, we need not mention the first medium. For first medium is vacuum all times, and absolute refractive index is represented as say mu a. Mu a means refractive index of the medium, absolute refractive medium A. In that case, on the left side, you need not write anything. You need not write vacuum. So mu A represents absolute refractive index. We tell mu 1 it is absolute refractive index. Refractive absolute refractive index medium 1. Mu glass absolute refractive index of glass. This is all. Now one thing, absolute refractive index of medium is always greater than 1. This is very important. Relative refractive index may be greater than 1, may be less than 1, but absolute refractive index is always more than 1. Why? Actually, whenever a light ray is refracted obliquely from vacuum to another optical medium. So here, vacuum is the rarest among all optical media. Vacuum is the rarest among all optical media, and so whenever light ray is refracted from vacuum to any other optical medium, the refracted ray will always bend toward the normal. And so, in that case, the angle of refraction is always less than the angle of incidence. That is, I is always more than R for absolute refractance. So, I is always more than R. So, sin I is always more than sin R. For we know greater the value of the angle, greater the value of sine. So, as I is more than R, sin I is more than sin R. And so, in that case, the ratio of the sin I by sin R obviously will be more than 1. And that's why I am telling the absolute refractive index of medium is always greater than 1. This is important, and sometimes this is also asked in the exam. Now, these are absolute refractive index. Now, generally, we tell refractive index. Sometimes we tell refractive is a medium. I am not it is absolute or relative. If we tell only refractive index of medium, it means refractive index with respect to AR or absolute refractive index. Actually, the velocity of light is almost or equal in vacuum and air. So whenever we tell the refractive index of medium, we mean it is with respect to air or with respect to vacuum, and they will not be different much, and therefore or they are more or less same. So whenever we tell refractive medium, we mean the refractive index with respect to air. This we tell refractive index of glass. It means that refractive index of glass with respect to air or absolute refractance of glass is same, almost same. Now, one thing, what is the effect of is that stating Snell's law? I told you the for a particular color of light. This particular color of light, the why actually there is a effect of color of light on the refractive index. The value of refractive index should not be same for all colors of light, and it will vary from color to color. Among 7 visible colors, the wavelength of least is for violet and greatest for red light. And for red light, the refractive index of a medium is least. For red light, it is least, and for violet light, it is the largest. So actually, and other colors they are arranged in order. In order, it will come the value of the refractive index. So I am telling refractive index of a medium means refractive index with respect to air or absolute refractive index of a medium is the greatest for violet light and the least for red light. However, if we consider the refractive index of a rarer medium with respect to a denser one, in that case, it will reverse. Actually, then it will be greatest for red light and least for violet light. If we consider the refractive index of a rarer medium with respect to a denser one. But generally, I told you that refractive index means refractive index with respect to air, that is a from rare to denser medium, or absolute refractive index. So in that case, it is greatest for, if it is asked in the exam, for which color the refractive index is the greatest, obviously for violet. You have to write for violet and is the least for red light. This is the effect of color on the refractive index. Now, some information I am telling, they are giving you some informations. One thing, I told you that the optical density, previously I told you the optical density in terms of velocity of light. But optical density from now on will measure optical density in terms of refractive index. Refractive index, actually optical density is measured with the refractive index. Greater the value of refractive index or the greater the value of mu is the optical density of a medium, is the one person important. Greater the value, actually AR mu glass is 1.5. AR mu water is 1.33. So you see, refractive index of glass is 1.5, refractive index of water is 1.33. So you can tell the glass is optically denser than water. And so the greater the value of mu, more is the optical density of the medium. Another thing, from the value of the relative refractive index, we can easily tell which one is denser medium and which one is rarer. Suppose I am telling AR mu water is 1.33. 1.33 is more than 1. And so it is more than 1. And so the water is denser than air. If you tell A mu be more than 1, so B is the second medium. So B is optically denser than A. But if A mu B is less than 1, then A is optically denser than A. So whenever a light ray is refracted from a rarer to denser medium, value of the refractive index of the denser medium is with respect to rarer one is more than 1. And whenever light ray is refracted obliquely from denser medium to rarer one, the refractive index of the rarer medium with respect to the denser one is less than 1. That is why I am telling, if MUB is more than 1, then B is denser, and if MUB is less than 1, then A is denser. This is how just by seeing the value of the refractive index, you can tell which one is rarer medium and which one is denser medium. Another thing, relation between A mu B and B mu A. The relation is simple. A mu B is equal to 1 by B mu A. Or B mu A, I am just writing here. You can see, you see, B mu A is equal to 1 by A mu B. And actually, the proof is not required for you. It will come from refraction, from the principle of reversal of the light path. It can be obtained. However, you have to know the relation. B mu A is equal to 1 by mu B. So, just knowing one, the other can be obtained. As for example, air mu water is 1.33, that is 4 by 3, roughly 4 by 3. So, water mu air, refractive index of air with respect to water is 1 by 1.33, that is 3 by 4, that is 0.75, roughly point. Air mu glass is 1.5, that is 3 by 2. So glass mu air is equal to 1 by 3 by 2, that is 2 by 3, that is 0.67, like that. So this is how the knowing one, the other can be obtained like this. So this is a relation between A mu B and B mu A. Next topic is our angular deviation by refraction. Angular deviation by refraction. Angular deviation by refraction, previously I told you, whenever a light ray is refracted from obliquely from rare medium to denser medium. What is angular deviation? Just definition I am telling, it is given in your book. We just try to follow. Angular deviation means whenever light ray is refracted or reflected. The reflection, in case of reflection, it also deviation occurs. In case of reflection, refraction, whenever there is reflection or refraction, there is change of course of the light ray for normal incidents. For other than normal incidents, there is change of course of light ray. The change of course, in case of refraction save, it is change of course for oblique incidents. Now, this change of course is called deviation. This change of course of a ray of light during reflection or refraction is called deviation. Now, angular deviation is the angle between the original direction of the ray and the change direction due to reflection or refraction. Today I am discussing about refraction. So, here the deviation means the direction, the change of direction of the ray due to refraction. So, here the angle between the original direction of the ray and the changed direction due to refraction, this angle will give you the deviation. You just refer the diagram. In this diagram, you see the light rays traveling from a rarer medium to a denser one. So whenever it is traveling from rare to denser medium, here the deviation is obviously, I told you that the original direction of the ray. So deviation is this angle. It is represented by delta. Represented by delta. So delta is the deviation, and actually this is the original direction of the ray, and this is the change direction, and this angle will give you the angle of deviation. So obviously in this diagram, delta is equal to I minus R. Delta is equal to I minus R. And in this diagram, the second diagram, when light ray is refracted obliquely from denser medium to rarer medium, the deviation here, the original direction of the ray is this one, and the change direction is this one. Original direction, the change direction, and the angle between these two is this one. This is delta. In this diagram, delta is equal to R minus I. In this diagram, the delta is equal to R minus I. This angle of refraction minus angle of incidence. In this case, it was I minus R. Here it is R minus I. And for normal incidence, as I and R both equal to 0, so there is no deviation. Actually, it is obvious, no change of course of the ray for normal incidence. So no change of direction occurs, there is delta is equal to 0. In general, for refraction, we can write delta is equal to I minus R. You see, this wavy minus represents both I minus R or R minus I. It can be represented like this. Delta is equal to, for refraction, the deviation delta is equal to R I minus R. That is, this minus sign, this wavy minus sign represents, you have to subtract the smaller one from the greater one. That is, it is either I minus R or R minus I. That is, result is always positive. The subtraction result is always positive. This is the implication of this minus sign, wavy minus sign. So this is how the deviation by refraction is represented. So this is deviation. Now one thing, deviation by refraction also depends on color, and that is why the refractive index depends on color. The deviation is greatest for violet color of light. Deviation is the greatest for violet color and least for red color. Deviation is greatest for violet color of light and least for red color. I told you that refractive index is greatest for violet color and least for red color. And similarly, deviation is also greatest for violet color and least for red color. This is the effect of color on the deviation. Now, in case of refraction, sometimes asked, what is the minimum deviation of a ray of light in case of refraction? In case of refraction, the minimum deviation of a ray of light is 0 whenever the angle of incidence is 0. Is the minimum deviation is 0 when the angle of incidence and angle of refraction both are equal to 0. In that case, I minus R or R minus R is equal to 0. Our next topic is about refraction. Sometimes it is also called, sometimes asked, sometimes it is AR mu glass is equal to 1.5. What does it mean? It means that obliquely we have to tell that when a light ray is refracted obliquely from air medium to glass medium, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is 1.5. You can tell I am not mentioning the color here. Actually, the effect of color on refractive index is very small. The value of the refractive index differs from color to color in after at 3 decimal places or 4 decimal places. And that's why first 2 decimal places do not hamper for different colors of light. And that's why whenever we tell about the refractive index, we generally do not tell about the color of light. For it is all nearly same for all colors of light. The effect of color is very small, negligible. And so whenever you tell refractive index of medium, generally we do not mention any color. A refractive index of water with respect to air, ARB water 1.33 means whenever a light ray is refracted obliquely from air medium to water medium, the ratio of the sine of the angle of incidence in air medium to the sine of the angle of refraction in water medium is 1.33. This is how we can tell these are the refractive index. Our next topic is a refraction through a glass slab. Glass slab or rectangular glass slab. It's a rectangular solid. We know rectangular solid glass slab. A glass slab is it has 6 faces bounded by 6 plane surfaces. A rectangular glass slab, and whenever light ray is refracted, any two opposite surfaces of the glass slab are considered as refracting surfaces. Generally, if we consider a glass slab, I'm just showing you. Suppose I am telling it's a glass slab. So it's a glass slab. There are 6 surfaces. This surface, this one, this one, this one, and this one, and that one. So 6 surfaces are there. It's a glass slab. And any two opposite surfaces are considered as refracting surfaces. These may be the refracting surfaces, these may be the refracting surfaces, and these may be the refracting. Generally, if the rectangular glass slab is like that, then we consider these are the refracting surfaces. This is one refracting surface, this is another refracting surface. And whenever light ray is refracted through a glass slab, the refraction occurs, and whenever refraction occurs through a rectangular glass slab, I am just showing you. Just a minute. You see the diagram in the book, there is a rectangular glass slab. So we can show that refraction through any glass slab, and whenever there is refraction through a rectangular glass slab, no deviation of light ray occurs. This is important. And sometimes it is asked in the exam, show that for refraction through a rectangular glass slab, the incident ray and the refracted ray, that is emergent ray, both are parallel to each other. And the proof is given in your book. I'm just trying to understand you, to make you understand. Suppose the rectangular glass slab is this one. I'm just drawing the diagram. Just wait a bit. You see, The rectangular glass slab, and this is the incident ray. This is one refracted ray. Actually, there will refraction will occur twice. Refraction will occur twice. Refraction from air medium to glass medium, and from glass medium to air medium. This is glass. Here is glass. Is air, and there is also air. So light ray is getting refracted from air medium to glass medium and glass medium to air medium. So whenever it is refracted from air medium to glass medium, refracted ray will bend to the normal, and whenever it is refracted from glass medium to air medium, refracted ray will bend away from the normal. So this is the incident ray, and this is called emergent ray. Sometimes it is asked in the exam, you have to show proof that PQ is parallel to RS. It is incident ray and emergent ray are parallel to each other. The proof is very simple. Actually, this is the angle of incidence. I am telling I, this angle of refraction R, and actually you see the angle of incidence is I here, and angle of refraction is R here. Now, rectangular glass slab, this surface, this plane and this plane, they are parallel, and these are the normal drawn here. These are two normals. The normals are also parallel. Therefore, you see this QR, this line. So these two normals are parallel, and this line, the refracted ray that is QR, is a transversal. So obviously this angle and this angle are equal alternate angles. So this, if this is R, this is also R. So this angle of incidence I, angle of refraction is R. Here the angle of refraction is, the angle of incidence is again R. And suppose the angle of refraction is here, is I dashed. I am considering angle of refraction is I dashed here. So angle of incidence I, angle of refraction R, angle of incidence is again R, for they are equal alternate angles, and the angle of emergence is I dashed, second refraction. Now for refraction from first medium to second medium, it is AR mu glass. I am writing first refraction. AR mu glass is equal to sin I by sin R. AR mu glass is equal to sin I by sin R. And glass mu air for second refraction, glass mu air is equal to sin R by sin I dashed. You see, for second refraction, glass mu air is equal to sin R by sin I dashed. Now, I told you earlier that air mu glass and glass mu air, one is reciprocal of the other. Therefore, we can write glass mu air is equal to 1 by air mu glass. 1 by air mu glass. That is sin R by sin I dashed is equal to 1 by sin I by sin R is equal to sin R by sin I. You see, glass mu air is equal to 1 by air mu glass. That is sin R by sin I dash is equal to 1 by sin I by sin R. That is sin R by sin I. Obviously, you see sin R, therefore sin I dash is equal to sin I. Therefore, sin I dash is equal to sin I. That is, I dash is equal to I. Sin R will cancel. So sin I dash is equal to sin I. That is, I is equal to, I dash is equal to I. So as I dash is equal to I, obviously EQ is parallel to RS. EQ is parallel to RS. Thus for refraction through a rectangular glass slab, there will be no change of direction. Actually, the light ray is simply shifted, but deviation is not there. Incident ray and emergent ray are always parallel to each other. then its PQ is parallel to RS. So no deviation occurs by refraction through a rectangular glass slab. Only lateral shift of the light ray occurs. The light ray shifted laterally from its initial position. There is lateral shift occurs, but the incident ray and emergent ray are always perpendicular. The proof, and sometimes it is asked in the exam, the proof. And that's what I'm telling you. So thus for refraction through a glass slab, there is no angular deviation. Angular deviation is 0. Next topic is prism. Prism, prism generally we consider the triangle prism. Prism is a solid body bounded by a triangle prism I'm telling, bounded by three rectangular surface and two triangular surface. The prism will look like this. It is in your book, the diagram is shown. Since I said this is a prism. It is a prism like this. Prism. So two triangular surface. These are the two triangular surfaces and three rectangular surfaces. These are the three rectangular surfaces. This one, this one, this one, and this one. So it is bounded by five surfaces, two triangular surfaces and three rectangular surfaces. Now, any one of these rectangular two surfaces are called refracting surfaces. So these are the refracting surfaces. Suppose I am these are refracting surfaces, and this is called the base. So refracting surfaces of prism are those through which light ray enters and emerge from the prism. Through one of the refracting surface, light ray enters the prism, and through another refracting surface, it emerges out. And this is the base of the prism. This is the refracting edge. Refracting edge means the line where the two refracting surfaces intersect. The line of intersection of the two refracting surfaces is called the edge of the prism. Edge of the prism. This is the base of the prism, is the edge of the prism. Another thing is called prism angle. This is called prism angle, angle of the prism. This is the angle of the prism. This one is the angle of the prism. In the book diagram is shown in your book. So this is the angle of the prism. And or refracting angle is also known as refracting angle of the prism or angle of the prism. It's a very important thing, refracting angle. And another thing, principal section. If we consider any triangular surface or triangular section, if we cut a triangular section from the prism, it is called the principal section. Actually, while showing the refraction through a prism, in all diagrams, we show it with the principal section. For in principal section, we can see everything is present. I am doing the principal section. So say this is the principal section of prism. So this is the principal section of prism. This is the principal section. Principal section, this is the prism angle. This is the prism angle. The angle of the prism. This is the base of the prism. This is the base of the prism. And these are the refracting surfaces. So these are the refracting surfaces. This is the base. This is the angle of prism. So everything, refracting edge passes through this point, obviously. So these are the base angles of the prism. Now, while showing refraction through prism, we always show it by the principal section. This is very important. And in all diagrams, if you have to draw the diagram, you draw only the principal section to show the refraction through a prism. So we can show the refraction through a prism by principal section. And in your our syllabus, your the deviation due to refraction through a prism is generally asked. So one thing before telling about the deviation, prism I am telling the prism is generally made of glass in a laboratory. There are two types of prisms are generally found. Generally, mostly used. One is called equilateral prism. That is, all sides are equal, or the triangle of that equal. Equilateral prism, or another type of prism is called right angle isosceles prism. That is called total reflection prism. By that prism, we can show totalitarian reflection. It's called total reflection prism. There's two types of prism. So generally, we'll show with a equilateral prism. And in case of equilateral prism, I told you one of the rectangular surface is made base. Now, if the base is fixed, then it is generally made of ground glass. Otherwise, to reflect surface on ordinary glass. But generally, all are made of ordinary glass. No surface is ground surface. And generally, so in equilateral prism, any one of them can be considered as the base of the prism. Now, this is the principal section of the prism. Now, during refraction through a prism, so I am telling that the made of glass and outside medium is here. So whenever light ray will travel, we enter the prism, it will travel from rare medium to denser one, and obviously it will bend towards the normal. And whenever it will emerge out of the prism, it will bend away from the normal, and so the bending will be away from the normal. We'll show it. Now, suppose I am showing the refraction through a prism. One light ray is considered is incident on one surface, and after refraction, suppose it emerges out like this. I'm just drawing and showing it. This is the PQ. So you see, PQ is the incident ray, this is the refracted ray, and this is the emergent ray. Here is the emergent ray, the two refraction. Here air to glass, here air, it is glass, and it is again air. This refraction is taken from air to glass, and here from glass to air. Air to glass, glass to air. This is rarer to denser media. You can draw the normal. Suppose I'm drawing the normal here. You can understand. I'm drawing the normal. So these are the normals drawn here. You see the bending, light ray is bending toward the normal here, and light ray is bending away from the normal here. Now, total deviation. Actually, deviation occurs twice. In here, in case of first reflection, there is deviation. In second reflection, there is also deviation. The total deviation can be calculated. Now, I told you the deviation, angular deviation is the angle between the original direction of the ray and the change direction due to reflection or refraction. So, original direction of the ray, you can draw it. I'm just drawing with dotted diagram. The original direction of the ray is shown. And this is the change direction. I am drawing the diagram again, which is not clear. I'm drawing the second diagram. Wait a minute. I'm drawing a clear diagram. Is the principal section is ABC. You see, PQ is the incident ray, QR is the refracted ray, and RS is the emergent ray. You see the diagram clearly. Now, this is the original direction of the ray. and this is the change direction due to final refraction. So this angle will give you the deviation. This angle will give you the deviation. This angle. This is the deviation of the ray. This is the deviation delta. Now, this deviation can be calculated. Now, suppose I am telling this the book is given in your book. You can see the book. This is say R, this is R, and this is say I dash. You see the angle of incidence is given in your book. You can follow the book. I is the angle of refraction R, angle of incidence R dashed. This is R dashed, angle R dashed, and this is I dashed. So total deviation is delta is here. Total deviation. And suppose I am giving the name. This is D, this is E, and this is F. So total deviation is angle EFR. EFR is the total deviation. And obviously this total deviation EFR is equal to in this triangle FQR. In this triangle FQR, you see this is the exterior angle. Delta is the exterior angle EFR. So this angle is equal to two interior opposite angles. Sum of the interior angles, opposite angles, that is FQR plus FRQ. Now you see FQR is nothing but I minus R. FQR is nothing but I minus R. The group is given in your book. Just try to follow. So FQR is I minus R and FRQ is I dash minus R dash. So obviously the delta is equal to, we can write I minus R plus I dash minus R dash. It is I plus I dash minus R plus R dash. I plus I dash minus R plus R dash. This I plus I dash minus R plus R dash is a total division. Now, sorry, R plus R dash. I plus I dash minus R plus R dash. Now you see, you can show that R plus R dash is equal to A. This angle, the vertical angle, that is the angle of the prism. And that is shown here. You have to consider, you will see in the book, actually, that AQDR is a quadrilateral. Now, these two angles, that is AQD and ARD, these are 90 degree, each 90 degree. So, for these are normals are drawn. So, obviously, the angle A and angle D is 90 degree. Angle A and angle D 90 degree. I can write A plus D 90 degree. F plus D is equal to 90 degree. So, sorry, F plus D is 180, very sorry, 180 degree. These are 90 degrees, actually AQDR quadrilateral. Now the angle AQD and ARD each 90 degree. Therefore, the remaining angles, that is A plus D, is 180 degree. I wrote it here. A plus D 180 degree. Again, you see in triangle QDR, this triangle QDR, the sum of the triangles is 180 degree. Therefore, R plus R dash plus D is equal to 180 degree. R plus R dash plus D is equal to 180 degree. So comparing these two, we can write A is equal to R plus R dash. A is equal to R plus R dash. Comparing these two, that is A plus D is equal to 180 degree. Again, R plus R dash plus D is equal to 180 degree. Therefore, comparing these two, we can write A is equal to R plus R dash. So obviously, delta is equal to I plus I dash minus A. So this is the expression for deviation in case of refraction through a prism. This is the expression for deviation during refraction through a prism. I plus I dash minus A. So this is the expression. Now, deviation is a sum. If you draw a graph for deviation and the angle of incidence, then the graph will be like this. If we draw the angle of incidence and the deviation, angle of incidence is I and deviation that is delta. From this relation, A is equal to I delta is equal to I plus I dash minus A. From that relation, for a particular prism, that is for a particular value of A is fixed here. If we plot angle of incidence and delta, I and delta, then the graph will be as shown in the figure. The graph will be, you see, in this diagram, the value of delta, the increase of angle of incidence, initially it is gradually decreasing, and after a certain value, it again increases. Now, the graph is as shown for, actually you see, in the diagram, when refraction occurs, this is the incident ray and this is the emergent ray. Now, one thing, if you just reverse the arrows, then it will become the incident ray. This will be the emergent ray. This is called principle or reversibility of the light path. Principle of reversible light path. So, if this is the incident ray, this will be emergent ray. In that case, I dash will become angle of incidence. So, you see, deviation delta is equal to I plus I dash minus A. So, for angle of incidence I, the deviation is I plus I dash minus A. And if the angle of incidence is I dashed, then the angle of emergence become equal to I. So, in that case also, the angle of deviation becomes I plus I dash minus A. As you see, for same deviation delta, there are two angles of incidence, or for two angles of incidence I and I dash, the deviation delta is same, and that is why the graph is looks like this. So there are two values of I and I dash, for which the deviation will be same. Suppose I am telling the deviation delta, the angle of incidence is I, and here the angle of incidence is I dash. So you see in the diagram, so for say the delta is same for angle of incidence I, also for I dash. In expression also I told you that delta is equal to I plus I dash minus A. For a particular A, this prism is fixed here. So there are two angles of incidence, I and I dash, for which for both of them the value of delta is same, constant. That is delta. Now you see, if the value of I increases, the value of I dash gradually decreases, and at a particular case, the deviation is minimum. Deviation is minimum, generally represented as delta m. Deviation is minimum delta m for here in the graph it is here when I and I dash become equal. There is no difference of I and I dash. Actually, the value of I gradually increases, value of I dash gradually decreases. At this stage, at this point, I and I dash become equal and the deviation become minimum. So the condition for minimum deviation is I is equal to I dash. This is the condition for minimum deviation. Condition for minimum deviation is I is equal to I dash. Actually, from this graph, it is obvious when the deviation is minimum, I and I dash are equal. They are not different. And this is the condition for minimum deviation. So, in a prism, in a particular prism, that is refracting angle is fixed. In a particular prism, the angle of deviation is minimum when I is equal to I dash. The angle of incidence and angle of emergence both are equal. In that case, the angle of the minimum deviation will occur. And I told you that delta is equal to I plus I dash minus A. I plus I dash minus A. That is, so therefore, Therefore, minimum deviation delta m I is equal to I test. So we can write I plus I minus A, that is 2I minus A. So when the deviation is minimum, the minimum deviation angle delta is equal to 2I minus A. Delta m for minimum. So delta m is equal to 2I minus A. So this is how we can find the minimum deviation during refraction through prism. So this is expression for the minimum deviation. Now from that we can find the value of refractoriness. It is not our. The next topic will be the next one will discuss lens. The next topic will be lens. Now what is lens? Generally this first question there arises, what is lens? Lens is a transparent, homogeneous transparent optical medium bounded by two spherical surfaces or one spherical surface and one plane surface. That is, at least one spherical surface must be present. So lens is a transparent homogeneous optical medium bounded by two spherical surfaces or one spherical surface and one plane surface. This is lens. Lens is generally made of glass, but plastic lenses are also used. Fiber lenses are used in spectacles. You've seen it. You have seen it. So, what we'll discuss with the glass lens. So, in case of glass lens, there are in case of lens there are different mainly there are two types of lenses. These are convex lens and concave lens. Convex lens and concave lens. Convex lens and both are actually convex lens. Definition of convex lens. What is definition of convex lens? Given in your book. A lens which is thick at its middle and becomes gradually thinner towards its edge. The lens which is thick at its middle and gradually thinner towards its edge is called a convex lens. And the reverse one is concave lens, which is thin at its middle and gradually thicker towards its edge. This is called concave lens. In drawing diagram, we always take the side view of the lens. Otherwise, we can't show the diagram of a lens. So, while drawing diagram, we always take the side view. So, convex lens can be drawn like this, and concave lens can be drawn like this. So, lens which is thick at its middle is a lens. It is thick at its middle and gradually thinner towards its edge. I am taking the side view. I am looking toward the side view of the lens, and it will look like this. Not from front view. Front view is nothing but a side view. The side view. The side view, this is a convex lens. From side view, you can easily understand the bulging of the surfaces. So, in case of convex lens, it is thick at its middle and gradually thinner towards its edge. In case of concave lens, it is thin at its middle and gradually thicker towards its edge. Now, convex lens and concave lens, they can also be classified. There are three types of convex lenses. One convex lens, both side convex. I am just drawing the diagrams. Three types of convex lenses. You see, there are three types of convex lens. This is called biconvex lens. Biconvex lens, both surfaces are convex surface. This is a plano-convex lens. One surface plane surface, another surface convex surface. And this is concavo-convex lens. One surface is concave, another convex. You can tell why is it convex lens, for it is thick. All of them, you see, the central part is thick, the mid portion is thick, gradually thinner to lens. So this is biconvex lens, this is plano-convex lens, and this is concavo-convex lens. It is convex lens, but one side is concave. Now, biconvex lens, if the two surfaces are equal, if both of them is equal curvature, then it is called equiconvex lens. Equiconvex, both are equally curved. If both the surfaces of a biconvex lens are of equal curvature, then it is also called equiconvex lens. And this is plano-convex lens, one surface plane, another surface convex. And this is concave or convex lens, one surface concave, another surface convex. Is essentially all these are convex lenses is also called meniscus lens. A concave or convex lens is also known as meniscus lens. Meniscus lens. Similarly, there are three types of concave lenses. I am just drawing them. I'm just drawing them and show. There are three types of concave lenses. Is a biconcave lens. This is plano-concave lens. The convexo concave lens. All are concave lenses. You see, in all of them, the mid portion is thin. It's thin at the middle and thicker toward the edge. It is one surface is convex surface, concave surface. The curvature of the concave surface is more here, and that's why it is a concave lens. And the curvature of the convex surface is more here, that's why it was a convex lens. So it is plano-concave, it is plano-concave lens, it is a biconcave lens, and it is convexo-concave lens. Now, here also, a biconcave lens may be a equiconcave lens when the curvature of both the surfaces are equal. If the curvature of both surfaces are equal, then it becomes a concavo, sorry, equiconcave lens. Equiconcave lens. The equiconcave lens, biconcave lens may be equiconcave lens. This is a plano-concave lens. The concavo, convex or concave lens. So these are the different types of lenses. Now comes some definitions regarding lenses. Some definitions regarding lenses. The first definition you mirror, you read center of curvature. Here also in case of lens, the definitions are given. I'm just telling the definitions. Try to follow. Center of curvature. The center of curvature. In case of mirror, there is only one center of curvature. Now, I told you a lens is nothing but made by two spherical surfaces or one spherical surface and one plane surface. So there is some sphere. Now the center of curvature of any surface of a lens, there are two surfaces. The center of curvature of any surface of a lens is the center of the sphere of which the surface is a part. The center of curvature of a surface of a lens is the center of the sphere of which the surface is a part. Now, if the two surfaces are spherical surfaces, there will be two centers of curvature. There are two centers of curvature and they are at finite distance. We can draw the two centers of curvature. You see, I'm just drawing the diagram. It's given in your book. Try to understand. I just you see this is the biconvex lens is considered. The center of curvature. This surface is the sun is the part of the sphere, and this surface is a part of this sphere. So these are the centers of curvature. So this is the center of curvature CUR, the center of curvature of this surface, and this C2 is the center of curvature of this surface. So there are two centers of curvature. Now one thing, if the one surface is a plane surface, then where will be the center of curvature? Now we can consider a plane surface is a part of a sphere of infinite radius. A part of a sphere of infinite radius. So we can tell the center of the sphere of which the plane surface is a part is at infinity. So the center of curvature of a planoconvex or planoconcave lens, the center of curvature, one surface is at infinite distance, or one surface for spherical surface is at finite distance, and for the plane surface it is at infinity. Next definition is radius of curvature. The radius of curvature is similar definition. So the radius of curvature of any surface will have the radius of the sphere of which the surface is a part. So radius of curvature we can draw in the diagram. These are the radii of curvature of the two surfaces. These are the radii of curvature of the two surfaces. R1 and R2. They may be equal. The two are equiconvex lens or equiconcave lens. Two radii are equal. The radius of curvature, you can show radius of the sphere of which it is. Now, if one surface is plane surface, the radius of curvature of this surface is obviously infinite radius. Next one, its definition is principal axis. What is principal axis? Principal axis is the imaginary line passing through the two centers of curvature of a lens. The imaginary straight line passing through the two centers of curvature of a lens is called its principal axis. Now, if C1 and C2 be the centers of curvature, we can draw the principal axis like this. It is not a line segment, it is extended up to infinity. So the straight line passing through the two centers of curvature of a lens is called its principal axis. It is for convex lens or for any lens. The straight line passing through two centers. Now, the question is that if it is a planoconvex or planoconcave lens, then how can you draw the principal axis? In that case, you see the principal axis can be drawn like this. I am just telling you. Suppose I am consider a planoconcave lens. So planoconcave lens is drawn here. The center of curvature of the concave surface is here. See, and the center of curvature of the plane surface is at infinity. So in that case, you have to draw the principal axis. The principal axis of a planoconvex or planoconcave lens is along the direction of the normal drawn from the center of curvature of the curved surface on the plane surface. I am telling you again. The principal axis of a planoconvex or planoconcave lens is along the normal drawn from the center of curvature of the spherical surface on the plane surface. So obviously you can draw the diagram like this. So you have to drop the normal or perpendicular from the center of curvature of the spherical surface on the plane surface. This is how we can find the principal axis of a planoconvex or planoconcave lens. The next definition is optical center. In case of mirror, it was pole. In case of lens, it is optical center. In case of mirror, all distances are measured from pole. And in case of lens, all distances are measured from optical center. And that's why optical center is important. Now, optical center, the general definition is there. I first tell you the general definition. Just try to follow. We'll tell the definition. Now, just try to follow. Suppose I am considering a convex lens. Suppose for our simplicity, sake of simplicity, consider a biconvex lens, equiconvex lens. I am drawing the diagram. First, try to understand. Then we will tell you the definition. Suppose a light ray is incident on any refracting surface of a convex lens. And after two refraction, this air to glass, glass to air, bending to the normal, bending away from normal. So here, after two refraction, this is the emergent ray. So this is the incident ray, the refracted ray within the lens is the emergent ray. Now, if the incident ray and emergent ray are parallel to each other, then the path of the light ray, but the refracted ray within the lens must pass through a fixed point on the principal axis. This point is called optical center. So whenever a light ray is refracted in one surface, and after two successive refractions, if the emergent ray becomes parallel to the incident ray, if the emergent ray becomes parallel to the incident ray, then the path along which the light ray travels within the lens intersects at a point on the principal axis, and this point is called optical center. I am telling the definition like this. Optical center of a lens is a point on its principal axis fixed with respect to the lens such that light rays, parts of which PATHs, parts of which within the lens pass through that point, have their corresponding incident and emergent rays parallel to each other. I am telling the definition again. Optical center, actually, optical center of a lens is a fixed point, and it is a fixed point for a particular lens. It cannot be any point. It is a fixed point. The optical center of a lens is a point on its principal axis. It must lie on the principal axis. Fixed with respect to lens. It is fixed for a lens. Fixed with respect to the lens. Such that light rays, the parts of which, the parts of the light rays, the parts of which pass through that point, that is pass through the optical center, must have their corresponding incident and emergent rays are parallel to each other. I think it is clear. That is, if the incident and emergent rays are parallel to each other, the path of the light ray within the lens must pass the optical center on the principal axis, or must cut the principal axis at its optical center. Now, one thing is very important. This optical center may not lie within the lens. The definition is correct. The optical center may lie inside the lens or may lie outside the lens. For if the lens is equiconvex or equiconcave, optical center is the midpoint. It is in between the two spherical surfaces, obviously. But if the two surfaces are not equally curved, if the curvature of the two surfaces are different, then the optical center will not be the midpoint. Now, it will lie outside the lens If we consider a meniscus lens, that is convex or concave lens or concave or convex lens, the optical center will lie outside lens. But the definition will not be incorrect. The definition I gave you is correct for all types of lenses. The, the point of the principal axis is fixed with respect to lens, such that light rays, parts of which within the lens, it may not cut the principal axis inside the lens. It may cut the principal axis outside the lens also. But the path of the ray within the lens must pass through the point if the incident ray and emergent ray are parallel to each other. This is very important. So, optical center may be within the lens, may be outside the lens. If it is a plano-convex or plano-concave lens, it lies on the surface of the lens. And if it is convex or concave or convex lens, the optical center lies outside lens. So optical center is a fixed point with respect to lens. It may lie within the lens, it may lie outside the lens. This is very important. Now, whenever you draw the diagram for optical center, it is better to consider equiconvex or equiconcave lens. I will just draw the diagram. I drew the diagram here with equiconvex lens at the midpoint. Now, if you see, if the lens is thin, now one thing is, see, this is the incident ray, this is the emergent ray. In case of reflection through a lens, when the incident ray emergent ray are parallel, there is no deviation. Angular deviation is zero. Here also lateral shift occurs. It is shift, lateral shift occurs, laterally displaced. The light ray is not deviated. By refraction through a lens, whenever the light ray passes the optical center, there is no deviation. Lateral shift is there, but there is no deviation, angular deviation. For there is no deviation as the incident ray and emergent ray are parallel to each other. There is no angular deviation, but there is lateral shift. There is lateral shift occurs. Now, lateral shift occurs here. Now, one thing, if the lens is gradually thin, it becomes thinner and thinner. Lateral shift becomes smaller and smaller. Obviously, the incident and emergent will come closer. And for very thin lens, the lateral shift may be ignored. Lateral shift may be ignored. I can draw the diagram. I'm just drawing the diagram. For thin lens, so if the lens becomes very thin, the incident emergent ray come closer. The distance between them will gradually decrease, and for very thin lens, the lateral shift becomes almost zero, but it is ignored. In that case, the light ray passes directly through it. So, optical center for thin lens can be defined in other ways. Optical center for a thin lens is a point on its principal axis fixed with respect to a lens, such that light rays coming toward the point and refracting through the lens remain undeviated and undisplaced. Actually, undeviated here also, in this diagram also there is no deviation, but there is displacement. But here, both undeviated and undisplaced. So, optical center of a thin lens is a point on its principal axis fixed with respect to the lens, such that light rays coming toward the point and refracting through the lens remains undeviated and undisplaced. There is no deviation, there is no displacement. And this is the for thin lens optical center. Now, in our Madhyamik syllabus, all diagrams, image diagrams are drawn with thin lens. All image diagrams are drawn with thin lens. So, in case of thin lens, we can consider the optical center as a straight line, just the straight line passing through the optical center. no deviation or no displacement. It will go straight. If the light ray is refracted to the optical center, it will go straight, undeviated and undisplaced. In all diagrams of images formation by lenses, the, the light ray passing optical center was drawn straight without any deviation and displacement. But so optical center for thin lens is the point. And actually, if it is asked in the exam, define optical center, then it is better to draw the this diagram, the main actual optical center and the main definition with the thin lens for all lens. And if it is asked in the exam, define optical center for thin lens, then you draw this simple diagram, thin lens, and this simple definition. It will go straight without any deviation and displacement. The next definition of lens is focus. Principal focus. Focus of a principal focus of a. Actually, for lens, in case of mirror, you read one focus, principal focus. Principal focus is one. But in case of lens, there are two principal focus. Principal foci, this one plural is foci. There are two principal foci. One is first principal focus, another is second principal focus. Whenever we tell about the focus of a lens, we generally mean the second principal focus. So whenever it is asked in our Madhyamik syllabus, second principal focus is there, only second principal focus. Although I will just tell you the what is principal focus. The second principal focus means focus. So whenever it is asked in the defined focus of a convex lens, we write the definition of second principal focus of convex lens. So first, whenever you tell focus, this is second principle focus. So we'll give you first definition of second principle focus. Second principle focus. What is the second principle focus? Focus. Whenever a parallel beam of light rays coming parallel to the principal axis of a lens is incident on it, then after refraction through the lens, the definitions are given in your book. You can follow book. After refraction through the lens, the light rays either converge to a point in case of convex lens or appear to diverge from a point in case of concave lens on its principal axis. This point is called second principal focus or focus of the lens. I'm just trying to make you understand the diagram. These are given in your book. You can follow your book. Suppose I am consider a convex lens. Now one thing is very important. Refraction or during refraction of convex or lens, refraction occurs on both surfaces. But for our convenience, and actually bending of the light ray takes place from both surfaces. But in drawing diagrams with lenses, the bending is drawn from the central line. The central line is drawn and all the bending are shown from that central line in line. This is correct. In all diagrams of image formation, you will see that the bending of the light rays are drawn from the central line. So this is the principal axis. I'm just drawing the diagram. So it is a parallel beam of light rays. So convex lens. A parallel beam of light rays coming past the principal axis. Along principal axis, one light ray is directed, so it will go straight. For the definition of a thin lens you consider, so it will go straight. So optical center will go straight, and other rays are bending toward the principal axis and actually meet at a point on the principal axis. And in case of concave lens, I am drawing the diagram. The central line is drawn here also, You see, in concave lens also, that is the parallel beam of light rays. So definition will follow. If a parallel beam of light rays coming parallel to the principal axis of a lens is incident on it, then after refraction to the lens, the light rays either converge to a point, here converging to a point in case of convex lens, or appear to diverge my point. Actually, the light rays after refraction appear to diverge. You have to make it dotted. Actually, light rays are not there. The refracted rays are produced backwards. So they appear to diverge. The refracted rays appear to diverge from this point F dash F. So this in this case, the light rays either converge to a point in case of convex lens, or appear to diverge to a point in case of concave lens on its principal axis. This point is called second principal focus or focus of the lens. This is principal focus or focus of the lens or second principal focus. This is the focus. Now, next one is focal length. After definition of focus, the focal length. Focal length is, I told you earlier that in case of mirror, all distances measured from pole. In case of lens, it is measured from optical center. So, you see, the focal length in this diagram is distance between the optical center and principal focus. So, OF. OF is the focal length. OF is equal to focal length. OF is the focal length. In this diagram, both diagram, OF is the focal length. So, the distance between the principal focus and the optical center is called the focal length of a lens. So, in both diagrams, convex lens or concave lens, OF is the focal length here. Now, next definition is focal plane. What is focal plane? Focal plane, in just like mirror, the focal plane is an imaginary plane passing through the focus, principal focus, and perpendicular to the principal axis of a lens is called a focal plane. Achha, before focal plane I'm just telling. I told you the second principal focus. First principal focus, I'm just for this time I'm telling the before focal plane. What is first principal focus? The definition, it is not in your syllabus, but you have to understand what is first principal focus. Actually, the parallel beam of light rays after refraction meet at this point or appear diverse from a point at here. Now, if the arrows are reversed, then the point F becomes the first principal focus. The first principal focus of a lens is a point on its principal axis, such that light rays diverging from that point or light rays directed toward the point, diverging from this point in case of convex lens or directed toward the point in case of concave lens, after refraction become parallel to the principal axis. In case of convex lens, it is a point on the principal axis. If light rays after divergence from this point, after refraction become parallel to the principal axis, then this point becomes first principal focus. In case of concave lens, it is a point on the principal axis. Light rays directed toward the point, a convergent beam. If it is directed toward the point F, after refraction becomes parallel to the principal axis. So this is first principal focus. Actually, in case of lens, this one thing is important. Which one is first principal focus? Which one is second principal focus? This is not definite. This depends solely on the direction of the incident rays. If the incident rays come from this direction, then in case of convex lens, the second principal focus is this one, and first principal light on this side. In case of concave lens, if the light rays are refracted, come from this point, from this side, the second principal focus on this side, and the first principal focus on this side. Actually, it solely depends on the direction of the incident rays, which one will be first principal focus and which one will be second principal focus. And one thing is very important, the first principal focus and second principal focus both are equidistant from the optical center. What is the shape? Whatever be the shape, of the lens. What may be the shape of the lens? The first principal focus and the second principal focus are equidistant from the optical center. For any shape of lens, they are equidistant from the optical center. This is important. Now, they will not be equidistant. There is the two focal lengths. So the point is that two focal lengths on both sides of lens are equal independent of the shape of the lens. But the two focal lengths can differ only when the refracting media on the two sides of the lens are not equal. The two focal lengths of a lens become unequal only when the refracting media on the two sides of the lens are different. Suppose I am considering a lens, convex lens. On one side of the lens there is air, on the other side there is water. In that case, the focal lengths on the two sides will be unequal. This is the condition, only condition for unequality of the focal lengths, two focal lengths of a lens. When the two media on the two sides of the lens are different, only then the focal lengths become different. And I told you earlier, gave you the question, the focal length of a lens will differ when the medium changes. When a lens taken from, say, made of glass is taken from air under water, the focal length will increase. And I told you the reason. Actually, it depends on refractive index. Whenever it is taken under water, the refractive index, the index of lens material with respect to water decreases, and so the focal length increases. Actually, there is a formula. It's called lens maker's formula. From that formula, we can understand how does the focal length change with the change of medium. The lens maker formula, I'm just taking, that's for your interest, is taking the lens maker formula. Lens maker's formula. Lens maker's formula. You just see the formula 1 by, sorry, 1 by AF is equal to 1 by F is equal to mu minus 1 into 1 by R1 minus 1 by R2. And F is the focal length of the lens, mu is the refractive index of the lens material with respect to the surrounding medium. R1 and R2 are the radii of curvatures of the two surfaces of the lens. I am telling again, F is the focal length, mu is the refractive index of the lens material with respect to the surrounding medium. R1 and R2 are the radii of curvatures of the two surfaces. Now, it is obvious that greater the value of mu, less is the value of focal length. Or lesser the value of mu, greater is the value of focal length. I told you the focal length of the lens depends on the surrounding medium. So mu is the refractive index of the lens material with respect to surrounding medium. So if a glass lens, a lens made of glass, is taken from air under water, so water is optically denser than air, so refractive index decreases. So refractive index of glass with respect to water decreases. So the value of mu decreases, and so the focal length increases. Inversely proportional. So that is why whenever a lens made of glass is taken from air under water, the refractive index of the medium of the lens with respect to surrounding medium decreases, and so the focal length increases. That is why focal length of a lens increases when immersed under water. I told the answer, provided with answer later, earlier. Now, I told you the focal plane. Now, so I was studying focal plane. Now, focal plane is I told you the focal plane is the plane passing through the principal focus and perpendicular to the principal axis. This is focal plane. So in this diagram, we can draw the focal plane like this. This is the focal plane, and here also the focal plane. Actually, there are two focal plane on the two both sides. I'm just drawing the second focal plane. The focal plane for convex lens, the focal plane for concave lens. The imaginary plane passing through the focus and perpendicular to the principal axis. So, it is a focal plane. Now, focal plane, the next one is second principal, secondary focus. Next one is secondary focus of a